All right, hello everyone. Welcome to the next lecture. We are starting a new chapter today, right? Excited? Chapter number 12 of our textbook. This one. And this chapter is about Laplace transforms. So in this kind of, I've divided this chapter again, this lecture into again four shorter parts. So in this part, we are just going to kind of define what the Laplace transform is and what does it mean by a unilateral or a bilateral transform, and just introduce the step function. And in the next part, we are going to look at the example problem of a step function, and in the rest of the two parts, we're going to dig more deeper into the impulse functions. Step functions and impulse functions are very critical. So let's go into this entire chapter is about Laplace transform, right? And what is it we're going to learn in a second, but why it is and why we are learning this, because it is such a beautiful mathematical technique that we can use to solve a lot of the circuit problems, especially these RL, RC, RLC circuits that we have been solving in the past for the past 4 weeks, and doing the transient behaviors, natural response, step responses, and coming up with the second order, first order differential equations. We can solve a lot of that stuff in a much more simpler way by using this Laplace transform. So I had to teach the both the time domain solutions of those circuits, and now we are going to solve it through a Laplace transform as well, which is sometimes also known as a kind of a frequency domain. We have a time domain, we have frequency domain. Fourier transform is another frequency domain. Z transform is another frequency domain. Laplace transform is also sometimes commonly known as S domain analysis, but this is also frequency domain. Okay, let's get started. So it is why, again, I guess I kind of already very briefly talked about this, that when we were solving a lot of these circuits, RC, RL, RLC circuits, we were getting these differential equations, the first order, second order differential equations. And what we are going to realize in this chapter is, if I will convert those time domain differential equations into Laplace S domain, if I'm going to take a Laplace transform of those equations and convert them into S domain, my operations will become super simple. My equations going to become super simple, and they will be reduced to simple algebraic equations, and I can easily solve that. And I'm going to use these Laplace transform analyses to solve RC, RL, and RLC circuits and understand their transient behavior. And maybe we will do some of the examples very similar that we have solved in the past from our time domain analysis. Now we can do it in the Laplace or S domain analysis as well, and we can compare the results. The results should be exactly the same. Okay, so again, its key benefits are we can solve all of these first order and second order circuits in S domain rather than in time domain that we have done in the past. And it is much more easier again to operate these operate the circuits in S domain, or analyze the circuits more importantly in S domain. We can handle initial conditions much more easier and better, and we can analyze the transient responses too, which is going to become more clear shortly. So the point is, we get a time domain circuit, we can convert that time domain circuit into an S domain circuit, which practically means that I am transforming my time domain equation into an S domain equation. Once I convert that into a Laplace transformed equation, I can reconvert it back into time domain as well. So essentially, this is what we are going to do when we are going to do a circuit analysis. We will start with the time domain, move into frequency domain or Laplace transform, S domain, and then move it back to time domain. So let's get started to more specifics now. What exactly is a Laplace transform? Again, it's a mathematical tool where we are converting the time domain signals f of t into S domain functions f of s. They are usually denoted by a capital F, and essentially this is S, right? S indicates it's an S domain equations. And again, we talked about this. We can convert this integral differential equations into a simple algebraic equations in the frequency domain when we do it. So let me take sorry, what happened? Okay, so now let's assume a function f of t, which only exists for t is greater or equals to 0. So if I'm going to take a Laplace transform of f of t of this time domain signature right? How I can take a Laplace transform, right? What's the definition of a Laplace transform? So here's the definition of Laplace transform. This f of t is a time domain signal. You are taking a Laplace transform, so you kind of indicate like this, like you are with a capital L with parentheses of f of t, which is taking a Laplace transform of f of t. And once the Laplace transform will be taken, your output function is going to look like this, right? So this is a transform function, capital F of s, capital F, and again it is an S domain signal, so S. And the way to define it would be you multiply f of t, your original time domain signature, with an exponent e raised to power minus st, and then take an integral with respect to t, and then define the limits of integration. Over here, the limits of integrations are shown as 0 to infinity, and we will realize that we can potentially take it minus infinity to infinity as well. And I'm going to provide you both definitions in a second. But more importantly, for circuit analysis, we are okay just with 0 to infinity as well. I'm gonna talk more about this lower limit of integration in a second. But this is the basic definition of a Laplace transform. If you're interested in taking a Laplace transform of anything, multiply that function with e raised to power minus st and take a derivative with respect to t. Take an integral with respect to t. And that should give you a Laplace transform of that function. And in this chapter, we're going to calculate Laplace transform of so many different things. And then you're going to realize that your life is going to become much more easier in solving RC, RL, and RLC circuits. Your lower limit of the integral over here is 0. So the Laplace transform ignores the values of t, the values of f of t for negative values of t. Again, potentially, there are two different definitions for Laplace transform, unilateral and bilateral. I'm going to introduce that in a second. But the point is that for most of the circuit analysis, we don't care about the t values less than 0 or the negative values of t. As you have seen that in most of the time we are switching the circuit at time t is equal to 0 or greater than 0, right? So we can do the circuit analysis very well while defining the lower limit of integration on the Laplace transform starting with 0, right? So we only care about the behavior of this f of t for the positive values of t. Now again, if you, in this specific case where your lower limit of integration is 0, that is called as a one-sided or unilateral Laplace transform. However, mathematically speaking, there could be a bilateral Laplace transform where your integral is going to be minus infinity to infinity. And that is known as two-sided or bilateral Laplace transform where the lower limit is negative infinity. And this is how you can write it, right? So minus infinity to infinity f of t raised to 1. So rest of the thing is the same other than the lower limit of integration. And again, this is also f of s, which is kind of taking a Laplace transform of f of t. So this is known as a bilateral Laplace transform, and this is known as a unilateral Laplace transform. And as we are going to solve electric circuits, we are going to realize that we care about unilateral Laplace transform for the electric circuits rather bilateral Laplace transform. Interesting thing is that in a and another thing that we are going to learn is even while considering a unilateral Laplace transform, we will be able to take care of the initial conditions, right? We had this initial condition, initial inductor current, initial capacitor voltages, which in the time domain which we solve it for t is less than 0, solving the circuits for t is less than 0, right? So we are going to realize that we can solve all of that while still considering a unilateral Laplace transform and still incorporating the initial conditions. So just bear with me once we're going to get there. Let's jump more into it. What happened? I wanna kind of talk a little bit more about on the lower limit of integration on the unilateral response and initial conditions as well. Here are the two functions that I am showing you, right? So this is f of t and this is f of t. In this function, right, this is an exponent function, e raised to power minus at, and this function is defined for both t is less than 0 and t is greater than 0. And this function is continuous, right? This is a kind of a continuous curve that is coming in all the way over here. What is the value of f of t at 0? I know the value is exactly equals to 1, right? Now let's look at this function. This is also f of t, but this function is called a discontinuous function. Why discontinuous? Because less than 0, the value of the function is 0, right? And then greater than 0, the function is can be represented by this exponent, e raised to power minus at, right? But what is the value of 0 here? The value exactly at 0 is some sort of an ambiguous value. Because what is happening exactly at 0, the value is switching from 0 to 1, right? And this is kind of, by the way, abrupt changes that we're going to realize that shows the switching behaviors in our natural and step responses whenever we are turning on and turning off the switches. Anyhow, coming back to this function, so this function is a discontinuous function, and the value at f of 0 is ambiguous, right? Again, because you suddenly get this kind of a step from 0 all the way to 1, exactly at 0, right? So this kind of poses a question. If I am taking a Laplace transform, let's say of an f of t, so how should the Laplace transform handle this discontinuity, right? What shall we do at 0? And the point is, shall I include, since I define my unilateral transform at 0 to infinity, right, positive infinity, I wanna understand what to do with this discontinuity if I get a function like this thing. And in problem with the circuit analysis, that we are going to get functions like this because we have these switching behaviors going on, right? So the problem comes in that shall I include the discontinuity or exclude the discontinuity? And interestingly, if I am going to include the discontinuity, this means that I can start my limit of integration at 0 minus. 0 minus to infinity, right? Which means that this 0 negative indicates that I am picking a value just before 0, right? So just before 0 includes the discontinuity in this function, right? And if I were to exclude that, I would start my function from 0 positive to infinity. This means that I am excluding the discontinuity now, and I am starting my values of or limit of integration just after the 0, and the value is defined just after the 0. So it really comes down to, shall we include or exclude the discontinuity? And the answer to this question is we should. Anybody? I wish I would have been asking this in person. Yeah, we should include the discontinuity because, again, in the circuit analysis, we care a lot about initial conditions as well, initial inductor current, initial capacitor voltage. So when we are going to apply a unilateral Laplace transform for the time domain signals, in case of our RL, RC, RLC circuit analyses, we are going to consider a unilateral, not only a unilateral transform, we are going to include any such discontinuities at 0 or switching time. So our limits of integration is going to be 0 negative to infinity, and rest of the Laplace transform is kind of a standard function, right? F of t is to 1 minus st. Laplace transform of f of t is f of s. Okay, great. So this should clarify another kind of interesting concept. I want to introduce a couple of other terms. We are going to use it. We can take Laplace transform on the functions, on different functions. For example, I can take it on sine of omega t. I can find a Laplace transform of a function. Sine of omega t is a function. Cos of omega t is a function. T is a function. T squared is a function. E raised to power minus at is a function. Natural log of t is a function. So I can define a Laplace transform on a function, and that Laplace transform is known as a functional transform. Another definition is operational transform. I can also define a Laplace transform of a mathematical operator, right? So for example, an integral is a mathematical operation, right? Taking a derivative is a mathematical operation. So I can define the Laplace transform on the operations, mathematical operations as well, and that is known as an operational transform, right? So for example, if you are taking a transform of a derivative of f of t, this is known as an operational transform. If you're taking a Laplace transform of sine of omega t, this is known as a functional transform. So just again introducing a couple of other terms that we are going to use in the in the other lectures and the rest of the lectures as well. Let's talk about take a little bit more deeper on, since we are going to use this Laplace transform for our circuit analyses, right? We had the switching things going on, and then switching behavior is very interesting because as soon as you switch, there are abrupt changes in the current and the voltages in the circuit, right? So we are really gonna kind of try to understand the Laplace transform from that circuit perspective. And the problem is, that abrupt changes can potentially eventually be modeled as the step functions and impulse functions. So literally, this is we are not going to delve into a lot more taking Laplace transform of the functional transform or operational transform. We are going to keep it for the next lecture. In this lecture, all I'm going to talk about is this kind of switching and a step function and impulse function that are kind of related to those switching things, those abrupt changes that's been happening, right? As I've seen that in this function, right, your value switches from 0 to 1 right at time t is equal to 0. So we need to figure this thing out about this discontinuities in the functions. Okay, so step function. Let's consider a circuit with a switch. Again, when you are going to change the position of a switch, that will create abrupt changes in the voltages. So we can mathematically represent those changes as a discontinuity, which can occur at any time t. And we can represent those discontinuities again in current and voltages by step and impulse functions. So again, in this lecture, we are just going to talk about those step functions and impulse functions. Let's start with the step function. Here's a very kind of a typical step function, right? Again, this step function, as you can see, the step function is the value is of this function is, right? The value of this function is exactly 0 for t is less than 0 and exactly k for t is greater than 0. If this k would be value of 1, we would call it a unit step function. You must have heard the name before, right? If the value is 1, we call it a unit step function. Otherwise, the k represent the amplitude or the strength. No, not the strength, because that word is more associated with the impulse function. But k represents, let's call it the amplitude of the function, right? Again, that's a very simple function. What we are interested in, the kind of this thing. What is happening at time t is equal to 0? Again, we are moving from 0 to value of the k. And we have this kind of a discontinuity, right? So here's a kind of a mathematical representation of this function. F of t can be represented as k times u of t. And the value is exactly 0 for t is less than 0, as I've write all of this value. And the value is exactly k for t is greater than 0. Sorry. So here's your function, right? And if the value is 1, then you call it a unit step function. So the problem is, again, I am more interested in this discontinuity, right? About the switching behavior. So we wanna mathematically model it, and we wanna figure it out before we do any of the circuit analysis. Practically speaking, I know that in exactly 0 time, my values cannot move from 0 to k, right? So I need to mathematically model it. So the one way to possibly model is I am going to consider that in a very, very tiny interval of time, and that interval of time could be very, very tiny. Actually, it's 0 negative to 0 positive, just before 0, just after 0. During that time, the value from 0 to k just linearly increases. It can increase any other way as well, potentially, right? But we need to model it, and we're going to model, for example, as a linear approximation first, right? So we cannot define the step function at t exactly equals to 0 because we don't know what is happening exactly equals to 0. Other than the values going from 0 to 1. So which value are you going to consider? The value at 0 is ambiguous, right? So we are going to consider, kind of zoom in into the 0, and we're going to define just before the 0 at 0 negative, just after the 0 at 0 positive, and then we are going to assume that the value of the step function just ramps, right? So just imagine you operated the switch on and off. There is some circuit variable, some current or voltage, right, that starts to go up or down, right? For example, if the value is increasing from 0 to k, it is going up. And we can assume that going up from 0 to k as kind of a linear operation. So if we assume the transition from 0 to 0 positive as a linear transition, we can kind of model this thing with a linear approximation, which is over here. So you can see that this is kind of a zoomed in thing, right? Very heavily zoomed in. 0 negative is very, 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 very small, and 0 positive is very small as well. And I can see that from 0 negative to 0 positive, right, we are moving from a value of 0 to k. So we move in between 0 to k in between 0 negative and 0 positive. If we are moving, if the delta t in between 0 to 0 negative is the same as 0 to 0 positive, then exactly in this linear approximation, I am going to hit the value of f of t as 0.5k. I'm only going to cover half of the amplitude, right, in this linear approximation. And assuming slope equals to 1. Okay. So this is kind of a linear approximation. What I'm going to do is I'm going to kind of finish the lecture over here, and I'm going to talk more about the step function. We are also going to do an example of a step function as well. We're going to also look at step function a little bit more in the next part of the lecture. Again, in this part of a lecture, the objective was just to introduce you with what a Laplace transform is. Laplace transform converts the time domain signal into the frequency domain and is going to make our life easier because all of our differential equations are going to become simple algebraic equations in the Laplace domain or S domain, right? And we kind of define this frequency. We kind of define this Laplace domain, Laplace transform as f of t raised to minus st and taking an integral. And then we saw that we are only interested in kind of a unilateral Laplace transform, and our lower limit of integration is 0 negative because we want to take care of initial conditions as well. Then we kind of discussed about the switching behavior, and that switching behavior we wanted to model it, right? Then in terms of modeling it, we will realize that the impulse function and step function both needs to be considered. So we started with the step function and saw that okay, step function has this discontinuity at t is equal to 0. We don't know what the value will be because it is jumping from 0 to k right away. And then but that right away is still some delta t, and that delta t was defined from 0 negative all the way to 0 positive, very very short interval of time. And in that short interval of time we defined that the value rises from 0 all the way to k, so the value at exactly 0 should be 0.5 of k. Okay, so with that, thank you so much. I'm going to talk to you in the next lecture. Bye.